so as a recap, there's two main applications of the line integral, of the integral over the curve of f times the tangent vector, unit tangent vector ds, which is f dot r prime dt. That's work and circulation. Now work is the work done by the vector field in moving an object along the curve. And the circulation is the amount of the vector field that is moving in the direction of the curve. Okay, they're very similar. It's just kind of a different philosophical way of framing it. And I will also say that your units will actually depend on which type of application problem you're looking at, right? So it just depends on, are we talking about the work done by an electromagnetic field, or are we talking about the circulation done by some kind of fluid setup with currents? It just depends. Okay, so let's see be the unit circle traversed once counterclockwise. Find the circulation for the vector field negative yx, or 0, 1 minus y squared. So the curve is staying the same. And I should have put arrows on the last one, sorry. These curves all have directions to them. So I should have drawn those on the previous page as well, that they had a direction. It was right here. I'll just kind of shove it in there. All right, so there it goes. Direction. All right, so these have direction. We're traversing once counterclockwise, which is nice for us because we know how to parameterize that. All right, so we're going to find the circulation, all right, gamma. Okay, well, first thing we have to do is parameterize our curve. So that's no problem in terms of r of t, right? We know what that would be. Because it's traversing once counterclockwise, we know that it's cosine t sine t. And since it's the unit circle, we know the radius is 1. So that makes it really easy. All right, so cosine t sine t, and we're obviously going from 0 is less than or equal to t, which is less than or equal to 2 pi. Actually, let me just kind of put that in here. I'll put it up here. All right, then we want to have the r prime, so we might as well find that right now because we're going to need it. So r prime of t is equal to derivative of cosine is negative sine of t, derivative of sine is cosine of t. Okay, so these two pieces are going to be the same for both curves. So I'm just going to kind of box them off because it's the same curve for both parts. Okay, now for part A, we need our vector field. Our vector field was negative y comma x, right? This is x, this is y. So negative y comma x would be negative sine t cosine t. All right, so now we want the circulation. The circulation is the integral from 0 to 2 pi, negative sine, I don't know what I'm writing there, negative sine of t, cosine of t, dot product with negative sine t, cosine t, dt. So that would be the integral from 0 to 2 pi of sine squared t. Oh, this is not a vector anymore, so don't draw it as a vector. It's a parenthesis. Sine squared t plus cosine squared t dt, which is, of course, the integral of 1 dt, which is t from 0 to 2 pi, which is 2 pi. And you can kind of see it when you look at it. You're trying to move around this curve, and that vector field is flowing with you, right? It's a rotational vector field. It's helping a lot. All right, I just wrote that in. Right, F is a rotational vector field. You can see it's rotating around. This is called the vortex a lot of times, right? So it's rotating around a vortex, and it's moving in the direction of the curve. And that's why our circulation is a big number, right? This is 6.28. Again, units are kind of not relevant depending, I mean, they're relevant, but we don't know what they would be. It depends on what your circumstances for this vector field. right? But either way, it's moving it a lot. Now, what about this one, right? It's going to be different, right? Because it's not moving with the curve. All right, so let's see what happens. So we're just going to draw a little line right here. All right, and let's look at part B. For part B, our vector field is 0, comma, 1 minus, and instead of y squared, y is sine of t, right? That part hasn't changed because it's the same curve as it was in part A. So it's going to be sine squared t. Okay. So now when we want the circulation, we want the integral from 0 to 2 pi of 0, comma 1 minus sine squared t. That's a vector. Dot product with r prime, which was negative sine t cosine t dt. All right, so when we dot product that, that's 0 to 2 pi. 0 times that is 0. So it's 1 minus sine squared t times cosine of t. And we're just going to make Maple do that. Right? We're not going to bother going to figure that out. Actually, before I go any further, I do want to note this is actually 1 minus sine squared. It's the Pythagorean identity. That's cosine squared. Right? Sine squared plus cosine squared makes 1. So this is actually the integral of cosine cubed t dt. All right, then I'll do it with Maple. And lo and behold, the answer is 0. Interesting. 0. Now, why did that happen? Well, if you look at the curve, you can kind of see it. So when you look at this vector field, for this section, it's pushing along, right? So it's going with the curve. So that's positive circulation. But over here, it's still pushing up, and you're trying to go down in this curve. So it counters everything. It becomes negative. And then over here, it's going against you, so it's negative, and then over here it's positive. So what's happening is it's pushing along and pushing away, right? It's pushing with you and then against you in equal amounts. So let me write that up. There. So the vector field is pushing with us and against us in equal amounts. And that means the positive circulation and the negative circulation end up canceling each other out, and you end up with 0.